Hello everyone, a very good morning to all. Today we will see the next module, compression member in steel structure. First of all, what is compression member? A compression member is one where the forces applied are trying to compress the member to push it together. Okay, what is compression structure? Compression structures are those structures on which compressive loads are applied along the length of the structure. So first of all, we will see the content of this chapter. Introduction, various type of sections used for compression members, column end condition and their effective length, Euler's theory, strength of an axially loaded compression member, slenderness ratio, and lastly compression member failures means buckling. Okay, first of all we will see introduction. Compression member is a structural member which is straight and subjected to two equal and opposite compressive forces applied at its end. Okay, see the second point. Different terms are used for a compression member depending upon its position of structure. First of all, which member is in compression? How to decide? Under the axial or compressive loads, a member deflects in a direction perpendicular to that of load. Then deflection occurs along the weaker of the two axes of the section. Some of the example of compression member: column, strut, post and top chords of trusses. See the second point, different terms are used for a compression member depending upon its position of structure. There are two types of compression member. First, column and second, strut. What is meant by column? It is a vertical compression member supporting floors and girders in a building. And what is the meaning of strut? It is a compression member used in roof truss and bracing. They are of small span and it may be vertical or incline. These compression members are subjected to heavy loads. The principal rafter. What is meant by principal rafter? It is the vertical compression member in a building. Okay. The principal rafter is top chord member in a roof truss and boom is a principal compression member in a crane. It means that a vertical compression member in a building are called as column and post, and a compression member in a roof truss. A compression member in a roof truss is known as strut and in a crane is known as boom. Okay. So, which is the best compression member section? Which is a best compression member section? Generally we have to use ISHB section, means Indian Standard Heavy Beam section, and unequal angles with short leg connected are preferred as compression member section. What is compression structure? Compression structures are those structures on which compressive load are applied along the length of the structure. Okay, this figure shows that compression member, it is a structural member which is straight and subjected to two equal and opposite compressive forces applied at its end point. Okay, this is the example of compression member. See this figure, we can see that there are some columns and beams. This is an industrial structure where in column, slab, beams are provided. In this structure, column is compression member because Load transmitted of slab and beam is taken care by column, and this load compresses the column member. Okay. Then we will see the common type of compression members. In addition to most common type of compression members, vertical members in structure, compression may include arch ribs, rigid frame members, incline or otherwise, compression elements in trusses. First of all, we will see steel frame with 3-hinge arch. So what is 3-hinge arch? It is geometrically stable and statically determinate structure. Okay. In the case of 3-hinge arch, we have 3 hinges, 2 hinges at support and 1 hinge at the crown, means top, thus making it statically determinate structure. A 3-hinge arch is a geometrically stable and statically determinate structure. It consists of 2 curved members connected by an internal hinge at the crown, and it is supported by 2 hinges at its base. It will not affected by the settlement. It provides an internal member or tie to resist outward thrust caused by arch action. Second, we will see steel rigid frame. This is the diagram of steel rigid frame. This is the common type of compression member. So what does rigid frame mean? In structural engineering, a rigid frame is the load resisting skeleton constructed with straight or curved members, and which are interconnected by mostly rigid connection on which resist moments induced at the joint of the members. Its members can take bending moment, shear and axial loads. Okay. So this is the diagram of steel rigid frame. And another example, this is the actual diagram of rigid metal framing. So what is the advantage of rigid metal framing? These structures can be constructed rapidly, and frame structures have economical designs. Economy is also very important factor in the design of building system. Okay. Then we will see compression member in trusses. Compression member of roof trusses are composed of single angles or double angles. These members may be continuous member. Double angle sections are very popular as compression members in trusses. This figure shows that third diagram shows that inclined members are known as compression member and horizontal member is known as tension member. So this is the common type of compression member. This is another example of compression member. So next point, sections used for compression member. Some of the various sections are used in compression member. See the first point. In theory, numerous shapes can be used for column to resist given loads. And second point, however, from practical point of view, the number of possible solutions is severely limited by section availability, connection problems, and type of structure in which the section is to be used. So we will see some of the sections of compression member. First of all, cross section shapes for rolled steel compression member. See diagram A shows that single angle section. Figure B shows that double angle section. C shows that T section. Figure D shows that channel section. Figure E shows that hollow circular section, and figure F shows that rectangular hollow section. So next, cross-section shapes for built-up or fabricated compression members. Figure A shows that closed channel box section with cover plate. Figure B shows that open channel section of box section. Figure C shows that open channel section of box section with cover plate. Figure D shows that plate eye section. Figure E shows that built-up eye section, and figure F shows that built-up box section. Okay, these are the cross-section shapes of built-up member. The next point we will see column end conditions and effective length. There are 4 cases of column end conditions. First case is the both ends are hinged. Second case, one end fixed, other end free. Third case, one end fixed and one end hinged. And fourth case, both ends are fixed. See the diagrams of column end condition and how to calculate the effective length when the radius of gyration is here. So first condition is pin ends, means both ends are hinged, where the k is equal to 1 and L effective means effective length is equal to L. Figure A shows that effective length is equal to L. See the middle, L is equal to L suffix E, forces applying on their end points, and when where k is equal to 1, k means radius of gyration. See figure B shows that one end fixed and other end free when effective length is equal to 2L and k is equal to 2. See the figure C shows that both ends are fixed when effective length is equal to 0.5L and k is equal to 0.5. And figure D shows that one end hinge and other end fixed when effective length is equal to 0.7L and k is equal to 0.7. So next point, assumptions, Euler's theory. Assumptions, Euler's theory. So what is Euler's critical load? This figure shows that critical stress versus slenderness ratio for steel for E is equal to 200 GPa gigapascal and yield strength is equal to 240 megapascal. Okay, this figure shows that critical stress. First of all, what is critical load? The critical load is the greatest load that will not cause lateral deflection, means buckling, for loads greater than Euler's buckling or crippling load. Therefore, it is clear that the maximum load at which the column tends to have lateral displacement or tends to buckle is known as buckling or crippling load. The critical load is the maximum load on which column can bear while staying straight. So we will see the assumptions of Euler's theory. First assumption, the material of the column is homogeneous and isotropic. Second, the compressive load on the column is axial only. The column is free from initial stress. Fourth, the weight of the column is neglected. Fifth, the column is initially straight, means no eccentricity of the axial load. Sixth, pin joints are frictionless, no moment constraint, and fixed ends are rigid, means no rotation deflection. And last, the cross section of the column is uniform throughout its length. Okay, so this figure Euler's theory, it is clear that the maximum load at which the column tends to have lateral displacement or tends to buckle, and the critical load is maximum load on which column can bear while staying straight. Slenderness ratio, which are indicated by L effective, means effective length divided by small r, is the radius of gyration, and this curve shows that Euler's buckling. Okay, so what is Euler's formula for critical load? It has mathematically expressed as PCR. P suffix Cr. Cr means critical load. Critical, and P means load. So Euler's critical load is given by pi square EI divided by KL whole square, where PCR is the Euler's critical load in bracket longitudinal compression load on column, and capital E is the modulus of elasticity of column material. Capital I is equal to minimum area moment of inertia of the cross section of the column. Capital L is equal to unsupported length of column, and capital K is equal to column effective length factor. See this formula, we can write PCR is equal to pi square EI divided by L effective square, because L effective is equal to KL. Effective length is equal to KL. See the conditions. The column fails only by buckling. This is true if the compressive stress in the column does not exceed the yield strength sigma y. So sigma is equal to PCR divided by A, where PCR means critical buckling load, is equal to pi square E divided by L effective divided by R whole square less than sigma y. See the second condition. For slender columns, critical stress is usually lower than yield stress and in elastic range. In contrast, a stocky column would have a critical buckling stress higher than the yield, that is, it yields in shortening period the virtual elastic buckling on set, where L effective by R is equal to slenderness ratio. L effective is equal to KL. L effective means effective length. R is equal to, R is the radius of gyration. So what is the radius of gyration? It has mathematically expressed as square root of I divided by A, where the I is area of moment of inertia and capital A is equal to area of cross section. See the end conditions of column. End conditions, there are 4 cases of end conditions of column. First, both ends hinge. So how to calculate effective length? Both ends are hinge. L effective is equal to L. See the second column. See the third column. How to calculate buckling load? For both ends are hinge in this condition. So P is equal to pi square EI divided by L square. Both ends are fixed. Second condition. How to calculate LE and buckling load? So LE is equal to L by 2 and buckling load P is equal to 4 pi square EI divided by L square. Third condition is one end fixed and other end free. So effective length is equal to 2L and buckling load P is equal to pi square EI divided by 4L square. And last condition, one end fixed and other end hinge. L effective is equal to L by square root 2, and buckling load is calculated by formula P is equal to 2 pi square EI divided by L square. So next point, how to calculate the strength of an axially loaded compression member. See this slide, maximum axial compression load permitted on a compression member. So P is equal to strength of axial compressive load is equal to sigma AC into capital A, where P is equal to axial compressive load in Newton. Sigma AC means permissible stress in axial compression. Sigma AC. AC means axial compression, sigma means permissible stress, which are expressed in megapascal mm square. Capital A is equal to effective cross-sectional area of the member. So we will see next point, Rankine's formula. See this formula. It is an empirical formula used for the calculation of ultimate load both for short and long columns. It gives the ultimate load that column can bear before failure. If column is short, then its calculated load will be known as crushing load, and if column is long, calculated load will be buckling or critical or crippling load. So how to calculate critical load? By Rankine's formula. See here, P is equal to sigma C into A divided by 1 plus alpha into L effective divided by R whole square, where sigma C is the critical crippling stress, capital A is the cross section area of the column, alpha is Rankine's constant, and it is equal to sigma C divided by pi square E. L effective divided by R is equal to slenderness ratio. L effective means effective length of the column, and R is the radius of gyration. So Rankine's constant of different materials. See material sigma C in MPa, and alpha is the Rankine's constant for different materials. Okay, you can see. So next point, slenderness ratio. What is meant by slenderness ratio? See the first point, the tendency of member to buckle is usually measured by its slenderness ratio. See the second point, slenderness ratio of member is the ratio of effective length to appropriate radius of gyration. It has mathematically expressed as lambda is equal to KL by R. Lambda is equal to KL by R, where L effective by R is equal to slenderness ratio. L effective is equal to KL. So we can write lambda is equal to L effective by R. R is equal to square root I divided by A. R is the radius of gyration. I is the moment of inertia, and capital A is the area of cross section. So next point we will discuss what is buckling. What is meant by buckling? When a slender member is subjected to an axial compressive load, it may fail by a condition called as buckling. When a slender member is subjected to an axial compressive load, it may fail by a condition called as buckling. From figure 1 shows that condition of buckling. Dotted line shows that original shape of the member, and bold line shows that buckled shape of the member. Okay. See, figure B shows that buckled steel column, and figure C shows that buckled RCC column. This is another example of column failure on actual field. Compression member failure. There are three basic types of column failures. See the second point. 1. A compressive material failure, very short and fat. 2. A buckling failure, very long and skinny. 3. A combination of both compressive and buckling failures. In bracket, length and width of a column is in between a short and fat and long and skinny column. Means combination of all columns. Compression member failure. There are three types. First type is the flexural buckling. Flexural buckling is also known as Euler's buckling. So what is meant by flexural buckling? It is the primary type of buckling members are subjected to bending or flexure when they become unstable. And second type of compression member failure is local buckling. So what is the local buckling? This occurs when some parts, see this figure shows that when some part or parts of X section of a column are so thin that they buckle locally in compression before other modes of buckling can occur. And last type of compression member failure is torsional buckling. What is torsional buckling? Torsion is the twisting moment. So these columns fail by twisting or combined effect of torsional and flexural buckling. This is the example of torsional buckling. Thank you.